Debugging Demo Part A quick introduction of the main concepts presented in this lecture. A hardware debugging tool is used to probe the state of a sketch running inside a microcontroller and provides assistance during a debugging session. The terminal window is similar to the familiar serial monitor in the Arduino IDE. It makes it possible to view text messages printed by the running sketch. You can use breakpoints to cause execution to stop at a specific line of code when that line is reached. You can use trace points to monitor the state of your sketch at a specific line without stopping execution. You can modify the default behavior of breakpoints and trace points by defining conditions and actions. For example, you can create log messages that contain variable values or calculate expressions. We are back in Atmel Studio, and in this lecture we'll go through an example debugging session using Atmel Studio. In the previous lecture, I simply created a project targeting the someday microcontroller on an Arduino Zero connected to the computer through its programming USB port, but we didn't really do anything other than creating the project, so we'll continue where we left off here. A good spot to begin is to make sure that we can actually upload this sketch to the Arduino without doing any debugging. So to do that, I'll just press the Start Without Debugging button. Just notice that there are two play buttons, two green play buttons. One is hello, this one here, which allows you to start the application, basically upload it onto the microcontroller and start it without starting the debugger. And then the other one is this one here, which will also compile and upload the sketch to the Arduino, but at the same time start the debugger. So let's start without debugging first. So the Arduino is getting flashed now. The application, the sketch, will be uploaded to the Arduino, and you can see that it's already started. The sketch is running on my Arduino Zero. Now, the Atmel Studio wants me to select a connected debugger tool and interface, and it's taking me to the relevant page in the studio to do that, and it's targeting tool. So you can see that there's a drop down here which allows me to select the debugger for my project. The only debugger that Studio was able to detect is the EDBG, which is this chip here on the Arduino Zero. If I had another external debugger connected, it would have detected that as well and given me the option to use it. In this case, it's only the integrated debugger, so I'm just going to click on that and choose it. I'm using the standard SWD interface for that, and that's it. You can see that up here in the studio, the options that I've just selected can also be seen and changed as well from here if necessary. So that's about it. I can save the project now, and let's start again with uploading the sketch. So build is successful and the project was uploaded. I can bring up the terminal window so I can see the output. The output from my Arduino is on COM5, I believe, so I select COM5. What about the baud rate? Let's go and have a look in my sketch. So it's 9600 bauds, so that this setting here is corrected, 9600, and connected. And there's my output. So output just works nicely. Now within the studio, I can fix these panes at different positions. So for example, you can get the little guides on the studio as you are dragging the window around, and they tell you where you can put things. So maybe I should put this little window, say around here. Alright, that tells me that it's going to be fixed at this point. I don't think it's a good idea. Doesn't look good. Maybe I'll put it down here actually. And just moving it around until I can lock it in place. Alright, there you go. So now it's locked in place. Alright, so with all that done, let's start with a sample debugging session. I can click on the solid green play button or hit F5 on your keyboard to get the debugger started. The program is now running on the SUMD microcontroller and the debugger is engaged as well. Let's start with the debug window. You can see that the debugger is running and the stop debugging button is available. I would like to set a couple of breakpoints. A breakpoint is a line in my code where the application will stop once it hits it. To set up a breakpoint, I can simply click on the side of the, I don't need this at the moment, I'll get back to that later. I can click on the side of the line. There's a little gray area here. We can also display the line numbers. I might actually enable line numbers. So I'll go to options and just search for lines inside the text editor. I believe that's where it's hiding. And general. So you go to all languages and there's the line numbers options, or enable that. Let's say that I want my application, my program or sketch to stop every time that the program reaches line 28. So I can just click on the side here and then I will enable this breakpoint. If you click on it several times, you can toggle between different states of the breakpoint. So in this case, I've got it enabled. You can see there's a little yellow arrow inside the red circle, and that indicates that the program has now stopped right here. It hasn't executed the command, the serial print command yet. The program has stopped there, and it's telling me that this is going to be the next command to be executed once I release the program again. You can also change the settings for the breakpoint, and you can set things such as conditions. I'll do that a little bit later. And I can tell it, for example, that I would like the program to stop at this line every time that it hits a multiple of, say, 5 hit counts. It means a hit count increases by, it's a counter that increases by 1 every time the program goes past this line in the code. So every 5 executions of line 28, the program is going to stop at this very point. Okay, scroll down a bit so I can see the rest. And I can get it to also do some actions, like, for example, every time that I go past this point or I stop this point, I'd like to print out a message such as I reached line 28. You can also evaluate expressions or print out variables. For example, you can see there's a counter variable here. I can print it out at this point using my curly brackets like that. Let's go to, we are already in output, and I'm going to hit continue, F5, and you can see that the program continues or restarts, actually not restarts, but continues where it left off on the microcontroller. And I got my message here, I reached line 28. You can see that then from 28 it went to 42 because of this multiple of 5 that are set up in the conditions. And then 5 line 28 executions. After that I get another printout and another printout and so on. Let's do something else. Have a look at the watches, for example. I can set a watch here. To set a watch, I need to temporarily pause or break the program execution. So with the program execution broken, I can go here and say, hey, I would like to have a look of the value stored in variable counter. So I just type in counter and at the moment it is 68. I can also look at other things, such as basically anything that is a variable or memory location. I can look into inside the watch. So for example, what is LED 1? So LED 1 contains value 3, and LED 2 variable contains value 4. So you can inspect the contents of variables like that. No print statements again here. It's just looking directly into a memory location. I can hit F5 to continue. Alright, so once I pause that, you can see the update of the counter is now containing the value 77. Let's set another breakpoint. I'll put a breakpoint inside, say, here. I can also right click and just set a point like that using the contextual menu. So here I can set a watch, I can set a breakpoint. Actually set a different kind of breakpoint called a trace point. So a trace point is just a point in the program where the program will not stop, continue execution, but it will just allow me to do something like print out a message without stopping the execution. So a little bit like what the println statements does in the traditional IDE debugging practice, traditional Arduino IDE debugging practice. Just looking at my context, I'm now in the block where counter divided by 2 gives us a 0 remainder, and that lights up LED 1. So at this point I'll just say print a message such as LED 1 is lit. And I can do the same thing down here. I'll put another trace point, and here I'll say LED 2 is lit. Okay, so we can continue with F5. I'm just going to hit F5 on my keyboard. And now you can see that when one LED lights up, then LED 2 is lit message comes up. When the other LED lights up, then LED 1 lit message is printed out. Great. Other little tricks that you can do is to inspect memory locations, which is another great feature that you get with a full debugger that you don't get with the Arduino IDE. So I'll stop, or I'll break execution here, and let's have a look at the watches. You can see that the watches make references to memory locations. So here, for example, we can see that the counter variable is stored at address, this one here, so 250 and C4. And the Atmel IDE, Atmel Studio IDE, gives you access to a memory tool. You can inspect what's inside every single byte location in the microcontroller. If I'd like to have a look at this location in the user memory of the microcontroller, I just need to type in its address. So let's go to C4, and I need to put a 2 at the front here, and that will take me to address C4. Right, so this 66 is address 250 C4. Now, because the SAMD microcontroller is a 32-bit microcontroller, every integer contains 4 bytes. So an integer is a 32-bit word in this type of microcontroller. In an Arduino Uno, which is using the Atmega 328, it's an 8-bit microcontroller, then the integer takes up 2 bytes, right? So now we've got 4 bytes for our integer. So these 4 bytes are used to store a value for the counter variable. When you're working with memory maps in Atmel Studio, it's a good idea to remember that in some of the microcontrollers, like in pretty much, as far as I know, all of Atmel's microcontrollers, words are represented in little endian notation. That means that the least significant byte is stored at the lower memory address. So in this example here, the lower memory address is this byte here, the C4 byte. And then we've got the 00, which is the most significant byte. Of course, the representations here are in hexadecimal. So I can convert this word into decimal just to confirm that we are really looking at a 102 decimal value. So I'll go and use my calculator, just a converter between hexadecimal to decimal. So I've got my hex value, which is 66 after 1, 2, 3, 4, 5, 6 zeros, and convert that, and we get a 102, which is the value that we can see in the watch monitor displayed. Similarly, you can find the value for LED 1 stored in location 08 right here. So you can see 03 hexadecimal, which is the same as 03 decimal, and these 3 bytes are stored for the LED. So by looking at this, I can obviously see that I'm wasting quite a few bytes here. I'm wasting 3 bytes. Not a big deal, since this is a small sketch, but in larger sketches you would look at minimizing the amount of space that I dedicate to storing the value for an LED, since I only really need just a single byte to do that. Another thing to consider while I'm still looking at the memory of my microcontroller is the memory map of the SAMD microcontroller. So I'd like to have a look at the documentation for the SAMD microcontrollers, and if you go down to page 43, you'll see the physical memory map table. And you can see that the internal flash, which is the place where your sketch gets uploaded, starts at location 0, and you get 256,000 bytes for your sketch. And then the static RAM, which is the part of the memory in the SAMD microcontroller where variables are stored during execution, start at this location. And you get 32 kilobytes of that as well. The Arduino Zero is using this variation of the SAMD microcontroller. So we get 256 kilobytes of flash for your application, and 32 kilobytes of static RAM to be used during execution. It's quite interesting to know. That's why here you can see that my counter starts at around 2000. I can go a little bit higher than that. Right, so this is the location where the first byte for my RAM exists. And these are undefined because these are programs. So if I go to the flash base, so you can see that the memory location here is all zeros. Then you can see the application represented in hexadecimals in memory, as it lays in memory, in machine code now, right? So I've got my sketch in a high level language, and then all that gets converted into machine code and uploaded into the microcontroller, and this is what the result looks like.